This video is going to focus on the mean value theorem for derivatives, and the reason why I chose that particular title is there's a mean value theorem for integrals as well. And so we want to kind of distinguish the two and say that, okay, this is for the derivative. If f is continuous on a closed interval AB and it's differentiable on the open interval AB, kind of like the way Rolle's theorem just started out, then there exists a number a number C in that interval AB such that the derivative of the function at C is equal to the slope of the line created by the endpoints. Okay, that's what that equation really says. That the value of the slope at that number C is the same as the slope of the line that connects the two endpoints, called the secant. All right, so now the tangent line refers to the derivative. The secant line refers to the line connecting the endpoints. So the slope of the tangent is equal to the slope of the secant. And so our first question is then, using this mean value theorem for derivatives, consider the function x squared plus 1. In part A, find the equation of the secant line joining the points -1, 2, and 2, 5. All right, so here's our part A. So we want to find that that equation. Okay, I'm just going to run through this just like we would anything else. First, I want to find the slope. The slope is equal to the difference of the y's, 5 minus 2, divided by the difference in the x's, which is 2 minus a -1. That equals 3/3, which is 1. Now I just choose a point, use point slope form, and that's it. So I get y minus 5 is equal to 1 times x minus 2, choosing the second point there. And this is it. This is all we need. That answers the question. It says find an equation for the tangent line. That's the equation for the tangent line. Now you can clean this up a little bit, and if you want to throw this in y equals mx plus b, you distribute the 1 and then add 5 to both sides, and so you get y is equal to x plus 3. That's an alternative form. It's not required though. Okay, so let's take part B. Part B says use the mean value theorem to determine a point C in the interval -1, 2. That is the interval. It is not the point. It's kind of nasty, I guess, to say, oh, there's a point -1, 2, and now there's an interval -1, 2. Yeah, but that's the way the problem read. So the interval -1, 2, such that the tangent line is parallel to the secant line. Parallel means they have the same slope. That is exactly what is being said here. That is precisely what is being said. Okay, so let's take a look at that then. We want to use the mean value theorem. That means that if you look, the slope, the derivative of the function at C, is equal to the slope. The slope of the function was 1, so we want to find out where the derivative is 1. In order to do that, we take the derivative. If f of x is equal to x squared plus 1, then the derivative is 2x. All right, so now we use all of that to determine where is 2x equal to 1. Well, where x is 1/2, and so if we put this back into the function, x is 1/2, f of 1/2 is equal to 1/4 plus 1, which is 5/4. So part B says, determine a point. Point is 1/2 5/4, such that the line is parallel, or tangent is parallel to the secant line. Part C says find an equation of the secant line through point C. Well, all right, we got a slope. The slope is 1. We have a point. That's it. Okay, so just write her down. C. We have y minus 5/4 is equal to the slope, which is 1, times x minus 1/2. If you don't like to leave it like this, you can go ahead and put it into the slope-intercept form. Simply distribute, just like we did above, and then add 5/4. So you get y is equal to, and your slope is 1, so it's x plus 3/4. And there it is. So it's really not too bad to use the mean value theorem. The mean value theorem simply says that the slopes of the secant connecting the points of the points on the function must be equal to the tangent line slope. Okay, that makes sense. We can find that. So it's not that bad. Just takes a little bit of practice. All right, that's the mean value theorem.